Welcome to part 2 of my series of videos on trigonometric identities. Let's start with the following identity, which says that the cosine of A times cosine of B is equal to the following. To see what this identity means, we put it in terms of sinusoids. And so if we have two sinusoids, the first with a frequency f1, the second with a cyclic frequency of f2, the above identity is telling us is that the result of multiplying these two together is that we generate the sum of two sinusoids whose frequencies are, the first has a frequency of f1 minus f2, and the second has a frequency of f1 plus f2. These are referred to as the sum and difference frequencies. In radio, these are referred to as upper and lower sidebands. Thus, if f1 is perhaps the frequency of your information signal and f2 is the frequency of the carrier signal, this trig identity is showing how we can translate our information signal up into the radio spectrum. And this is accomplished by simply multiplying the two sinusoids together. To see a demonstration of this, notice if I multiply first sinusoid frequency of 200 times a sinusoid frequency of 1000, the identity says that we should resultingly have a frequency of the difference, 800, and a sum, 1200 hertz, which we see here. This is how this signal would look in the time domain. Let's look at a second example and change the frequency of the first signal to 800 hertz. Multiplying these two together, now my difference frequency is shown by this spike, 200 hertz, and the sum frequency, 1800 hertz. The corresponding signal in the time domain looks as such. So the product of sum formulas, when we look at this, it's telling us we have a difference in sum frequencies. And notice, regardless of whether it's sines you're multiplying together or sines and cosines, you'll always see this pattern where you're getting a sum frequency and a difference term. Certainly one could just memorize this identity here, understanding what it means, and the others can be derived using the cofunction identity. As a second example, we're going to look at the case of where we are adding two sinusoids. And this tells us that we get, well, a frequency that seems to be the average here, and a frequency that is related to the difference. And let's look at this in terms of sinusoids and see what it says. So if you have two sinusoids that you're adding, what will happen, according to this identity, is if the frequencies are the same, well, this difference would be 0, and the cosine of 0 is equal to 1, so you simply get the same sinusoid on the output with double the amplitude. The interesting case is, though, is when the two frequencies are out of tune. And when that occurs, you have an oscillation here that's the average of those two frequencies, and the amplitude of that oscillation will be proportional to the difference. This frequency here, f1 minus f2 over 2, is referred to as the beat frequency. Let's look at an example of this. So here, if I am adding 440 hertz sinusoid to one that's out of tune, 444 hertz, we see the resulting time domain signal showing this envelope that's oscillating at the beat frequency, in this case 2 hertz. If we change one frequency, 442, we notice that they are not out of tune as much, and we see the corresponding change here. And of course, if you are in tune, you have the flat spectrum and just the one frequency component. Recall from part 1 that 440 cycles per second represents the A note right above middle C on your piano. Hey, let's see how this sounds. So if I'm tuning my guitar 440 hertz and it's out of tune, 442, let's see how it sounds. Now in this case, if it's 440 hertz, the B frequency would be a little higher. Let's listen. And finally, when they're in tune. I would like to conclude with an example taken from AC circuits. For a resistor, the instantaneous power is determined by multiplying the voltage times the current. Now for a resistor, the voltage and current are in phase. Thus, using the trig identity above, we find the resulting power looks like this, and there is a non-zero average term, and thus this will be the average power for the resistor. Now for the case of an inductor, my voltage is a cosine wave, but the current is a sine wave, as for an inductor, voltage leads the current by 90 degrees. They're not in phase. So when we use the identity above, we get this expression for the instantaneous power, which has an average value of 0. And we understand that to be true, as an inductor will not dissipate any power. So how do we interpret this instantaneous power term? Well, when the power is positive, the inductor is absorbing energy, and when the power is negative, it is returning energy to the system. I'd like to thank you for watching this video, and I hope it's been useful in demonstrating the value of understanding the meaning behind the various trigonometric identities. Until next time.